Imagine a time machine. Not one that sends you to the future, but one made of gold, built to uncover the universe's most ancient secrets. That, my friends, is the James Webb Space Telescope. Launched on Christmas Day 2021, the JWST is the most sophisticated and powerful space observatory ever built. And what it sees will rewrite our understanding of the universe and our place within it. Light, that cosmic messenger, takes time to travel across the vast expanse of space. It's a journey that can span millions, even billions of years, carrying with it the stories of the universe. The farther away an object is, the longer it takes for its light to reach us. This means that the light we see from distant galaxies is ancient, a glimpse into the universe's distant past. So when we look at distant galaxies, we're not seeing them as they are now, but as they were billions of years ago. It's like looking through a time machine, peering into the history of the cosmos. Think of it like this. Imagine looking at a star that's, say, 100 light-years away. You're seeing the light that left that star 100 years ago, a snapshot of its past. You're seeing the light that left that star 100 years ago. This concept helps us understand the scale of the universe and our place within it. Now, the early universe, just after the Big Bang, was a hot, dense soup of particles. It was a chaotic and energetic environment teeming with potential. As the universe expanded and cooled, those particles coalesced into atoms, mostly hydrogen, the simplest element. This process set the stage for the formation of more complex structures. Gravity then began to pull these atoms together, forming the first stars and galaxies. These early structures were the building blocks of the universe as we know it. This light from these ancient objects has been traveling towards us for billions of years. It's a journey that spans the history of the cosmos. But as the universe expands, light gets stretched. This phenomenon is known as redshift, and it changes the way we perceive distant objects. It's like stretching a rubber band. The wavelength of the light gets longer. This stretching shifts the light towards the red end of the spectrum. And you know what kind of light has long wavelengths? Infrared light. This type of light is crucial for observing the distant universe. It's invisible to our eyes, but not to the James Webb Space Telescope. This advanced instrument is designed to capture infrared light with incredible precision. JWST is specifically designed to detect infrared light, allowing it to see these incredibly faint and distant objects. It's like giving us a new pair of eyes to explore the cosmos. With JWST, we're not just looking back in time, we're looking back to a time when the universe was just a baby, taking its first steps. It's a window into the earliest moments of cosmic history. We're witnessing the birth of galaxies, the formation of the very first stars, the building blocks of everything we see around us today. This is the story of our cosmic origins, unfolding before our eyes. Now let's shift gears and talk about something a little closer to home, cosmically speaking, that is. I'm talking about exoplanets, planets that orbit other stars. These fascinating worlds are scattered throughout our galaxy. We've come a long way since the first exoplanet was discovered in 1992. Back then, the idea of finding planets outside our solar system was revolutionary. Now we know of thousands of these alien worlds, and we're discovering new ones all the time. Each discovery brings us closer to understanding the universe. But here's the question that keeps us astronomers up at night. Is there life out there? This question drives much of our research and exploration. I mean, are we alone in this vast cosmic ocean? The sheer scale of the universe makes it hard to believe we're the only ones. The James Webb Space Telescope is giving us our best shot yet at answering that question. It's a powerful tool designed to peer deeper into space than ever before. When an exoplanet passes in front of its star, some of the starlight passes through the planet's atmosphere. This phenomenon is known as a transit. By analyzing the light that passes through, JWST can tell us what the exoplanet's atmosphere is made of. This is called spectroscopy. We're talking about detecting things like water vapor, which is essential for life as we know it, methane, which can be a byproduct of biological processes, and carbon dioxide, a key component of many planetary atmospheres. Even oxygen, the very ingredients that we know are essential for life as we know it. Finding these elements could be a game changer. JWST can study smaller, rocky planets too, especially those orbiting red dwarf stars, the most common type of star in the Milky Way. These stars often have planets in their habitable zones, While JWST might not be able to spot little green aliens waving at us, it's giving us the tools we need to search for life beyond Earth like never before. The possibilities are endless, and who knows what incredible discoveries await us in the vast cosmic ocean. The journey has just begun, and the future is full of potential. Have you ever looked up at the night sky and wondered, where do stars come from? They don't just magically appear, you know. The birth of a star is a spectacular event, and it all starts in giant clouds of gas and dust called nebulae. Think of nebulae as stellar nurseries where stars are born. But these nurseries are shrouded in mystery, literally. The dust in these nebulae obscures our view in visible light, making it difficult to see what's happening inside. But remember how I said JWST is designed to see infrared light? Well, infrared light can penetrate that dusty fog, giving us a clear view inside these stellar nurseries. With JWST, we can witness the entire process of star formation in unprecedented detail. We can see the collapse of gas clouds, the ignition of nuclear fusion, the formation of protoplanetary disks, the swirling disks of gas and dust where planets eventually form. And it's not just about the stars themselves. By studying these processes, we're not just learning about the birth of stars, but also about the formation of planets and the evolution of galaxies. Now, while JWST is busy peering back to the dawn of time and searching for life on distant planets, it still finds time to explore our own cosmic backyard, our solar system. JWST isn't just a telescope for looking at distant objects. It's also a powerful tool for studying the planets, moons, and other celestial bodies that share our sun. Take the gas giants, for example, Jupiter, Saturn, Uranus, and Neptune. JWST can study their atmospheres in detail, tracking storms, analyzing their composition, and even peering into their depths. Imagine getting a weather report for Jupiter's Great Red Spot, a storm that's been raging for centuries. Or what about studying the rings of Saturn? Those icy particles dancing in a delicate gravitational ballet. And then, there are the icy moons of the outer solar system, places like Europa, Enceladus, and Titan. These moons are thought to harbor vast oceans of liquid water beneath their icy surfaces, potentially even conditions suitable for life. By studying these objects, we can learn about the formation and evolution of our solar system, and maybe even glean clues about the origins of life itself. Now let's talk about one of the biggest mysteries in astrophysics, dark matter and dark energy. These two components are believed to make up about 95% of the universe, yet we know so little about them. Don't let the names fool you. These are some of the most elusive and puzzling phenomena in the universe. Despite their names, dark matter and dark energy are not just dark. They are invisible and undetectable by conventional means. We can't see dark matter or dark energy directly. They don't emit, absorb, or reflect light, making them completely invisible to our eyes and even to our most advanced instruments. In fact, they don't interact with light at all, hence the name dark. This makes them incredibly difficult to study, but not impossible. But we know they're out there lurking in the shadows because of their gravitational effects on the things we can see. For instance, the way galaxies rotate and cluster together suggests the presence of unseen mass. So how does JWST help us study something we can't even see? The James Webb Space Telescope is equipped with incredibly sensitive instruments that can detect the faintest signals from the farthest reaches of the universe. Well, for starters, it can map the distribution of galaxies across the universe with incredible precision. This helps us understand the large-scale structure of the cosmos. By studying how galaxies cluster together and how their light bends around massive objects, we can infer the presence and distribution of dark matter. This bending of light, known as gravitational lensing, acts like a cosmic magnifying glass. This is called gravitational lensing, and it's one of the key tools we have for studying dark matter. It allows us to map out where dark matter is located, even though we can't see it directly. JWST can also help us study the expansion of the universe, which is thought to be accelerating due to the influence of dark energy. This mysterious force is driving galaxies apart at an ever-increasing rate. While JWST might not be able to shine a light on the true nature of dark matter and dark energy, it can provide valuable data that will help us refine our theories and get closer to understanding these enigmatic forces that govern the cosmos. The more we learn, the more we realize how much there is still to discover. Now let's delve into the realm of cosmic chemistry. The universe isn't just made up of stars and galaxies, it's also a giant chemistry lab, with elements being forged in the hearts of stars and scattered across the cosmos. And just like a detective analyzing fingerprints at a crime scene, astronomers can study the chemical composition of celestial objects to piece together their history and understand how the universe has evolved over time. That's where spectroscopy comes in. Spectroscopy is the technique of splitting light into its component wavelengths, like a prism creating a rainbow. By analyzing the spectrum of light from a distant galaxy, star, or nebula, astronomers can identify the elements present and even determine their abundances. JWST is equipped with incredibly sensitive spectrographs that allow it to study the chemical composition of celestial objects in unprecedented detail. For example, JWST can study the light from the most distant galaxies, those that formed shortly after the Big Bang, and determine their metal content. By measuring the metal content of early galaxies, we can learn about the rate of star formation in the early universe and how galaxies have evolved chemically over time. It's like having a cosmic chemistry set, allowing us to unravel the secrets of the universe one element at a time. The James Webb Space Telescope is not just a telescope, it's humanity's next great eye on the cosmos, promising to answer questions we haven't even thought to ask. With each passing day, JWST sends back breathtaking images and groundbreaking data, revolutionizing our understanding of the universe and our place within it. So tell me, what are you most excited to learn about? Let me know in the comments below.